Hi all. Thanks for coming. We're just going to give ourselves a few more minutes for people to arrive. So please hang in there. We're just setting up, and we'll start in a few minutes. Thanks. All right. Hi everyone. Hi Madhu. I think it's a good time to do a microphone test as well. Is your microphone working? Keep it on mute.
Can you hear me?
Yes, perfect. Okay, good. All right. So let's give it a few more minutes. People will arrive, and then we can go from there. Okay.
Sure.
All right. Hi everyone. How are you doing? So I do think we should start. It's 6 after 12. So today's talk will be given by Madhu, and so he's presenting a paper. In a sense, it's a practice for hopefully what will be a BMVC paper. So it was something that was submitted to BMVC, and it got good reviews. So probably, hopefully, it will be accepted. I'm just waiting for that confirmation. But and hopefully as well, like in the future, we are doing this in person. I think as time goes on, we will try and look at the possibility of holding this in person, or maybe a mix of virtual and person. But anyways, OK. Donc, je ne sais pas si je devrais répéter en français, mais en tout cas, donc aujourd'hui, c'est la présentation de Madhu. connaissez tous. Donc, il va présenter un paper qui a soumis à BMVC et a reçu des bons revues. Donc, j'espère que c'est une pratique pour sa présentation à BMVC. Donc, c'est ça. Et je voulais dire aussi qu'il y a eu des réflexions de notre côté sur la possibilité de refaire les séminaires en personne, donc graduellement. Et donc, on espère bientôt pouvoir faire un mélange de présentation en personne et en virtuel. Donc, c'est ça. So, Madhu, the floor is yours. Please present.
Thanks, Eric. Hi, everyone. So I'll be presenting this paper that we submitted to BMVC, and hopefully it gets accepted. So this paper is about holistic guidance for occluded person re-identification. So this was like a part of work for my PhD. So what I would maybe, before starting, I would just give a brief overview, what we could expect in this presentation, and then I can start presenting. So we'll start by describing what is re-identification, and then what is conventional re-identification, that is holistic re-identification, and then we go to a specific case of re-identification, that is occluded person re-identification. Then we would see on why we have to do occluded person re-identification and why is it important, and then we talk about the motivation, and then we explain our methodology. So re-identification is given a camera view and another camera view, and considering that a person walks across these cameras, and given a query, we are supposed to find match it with a set of galleries that could be either from the same or different cameras. So normally what a typical ReID system has a deep CNN feature extractor for the query, and we pass the query either a video clip or an image depending upon the application through the deep CNN. And if it's a video clip, we aggregate the features and then try to do a similarity matching with similar features from the gallery, or features extracted the same way with those of the gallery. So by this way, we actually try to match or search for people from bounding boxes extracted from different cameras. So basically, this is usually like a retrieval problem where we try to find a matching score for different set of pairs and try to find the ones and select the ones with the highest matching score. So what we call a holistic ReID is this assumption that in both the query as well as the gallery, we have the whole view of the person. So so basically, it means that we assume that the person probably did not change his clothes between cameras, and there's no much occlusion covering him. And basically, his view did not change much except for the pose or perspective change due to the difference in camera. And some of the challenges of holistic ReID are because as we know, human is a non-rigid structure. Human body is a non-rigid structure, so it's very difficult to just rely upon the overall structure of the person. And secondly, there could be variability in capture conditions. Probably there's one camera that is more towards the shade and there's less illumination, and that could be the query, and maybe the gallery could have a better illumination, and this difference in illumination could actually interfere with the overall matching. And often there is blur, as we know, and there could be some cases of occlusion, background clutter too, depending upon the application. So, and one big problem with holistic ReID is assumes that an individual's overall appearance is preserved in both the viewpoints, but in the real world, it's very hard to have this assumption satisfied. For example, it could be a crowded scenario, or maybe a camera fixed in the downtown where we have many people walking during the weekend, and often one person tries to occlude another person, or they get occluded by objects, parked vehicles, and so on. And therefore, techniques developed for holistic data, it's very hard to say that they would work in the real world because of these additional challenges that we have. So this is an example of holistic data. So the literature that do holistic ReID use kind of data that we see here. So these are two views of a person, and we can see the whole image remains intact, and we can hardly see any occlusion here. But in the real world, if you're extracting bounding boxes for person to the ReID, we can almost immediately see that in these two images, these are both are surveillance videos, that there is some occlusion here, and due to different people, and occlusion different, maybe because of an object, tree, and occlusion due to vehicles and so on. And in holistic ReID can be simply trained by just giving the identity for each person. It will be like the task of learning identity for the person. And once we learn the identity, we could just use the features that will use for learning the identity to the query, and for extracting query as well as gallery features. But in occluded ReID, in addition to overall identity-based supervision, we might also need additional inference for occlusion. For example, we may have to know what body parts are occluded and what part of the body is occluded. And this could actually help us to mask the region that is occluded and extract features from the rest of the region. Because as we know, occlusion is there could be a lot of diversity in occlusion. We have different shapes and color and size. So when you say a human body, it's easy to say, okay, at least it comes under, though it's not a rigid structure, at least it has a certain pattern. But when we say when we discuss about a human body with occlusion, it's very hard to define the pattern. So it's better not to learn the occlusion, rather mask it somehow, maybe with some method, and then try extracting features. In addition to that, we observed, like from previously from the literature too, we observed that while doing a regular ReID or holistic ReID, when we look at the activation maps of these CNN features that learn re-identification, they often focus on regions like shoulders or chest, and it makes sense because the pants are usually black or brown or dark colored pants, and they're not discriminative enough. So a regular ReID mostly tries to stick with the most discriminative parts. But when there is occlusion, there is a big chance that the most discriminative parts could be occluded, and so therefore the holistic ReID methods won't be able to solve this problem. So there is some related work. I'll just explain some, maybe present some related work in this field, and then we can go to the motivation. So there was a first work that was introduced by Chen et al. And in 2018, and they simply solved, in fact, they were one of the first papers in this field, and they simply solved occluded ReID by using artificially occluded samples and having a classifier to say whether it's occluded or not. So by this way, the features that train on re-identification are aware of occlusion, and they do not use any additional supervision. It's just the artificially occluded samples. And another method, though it is not very presented in particular for ReID, but it was actually used by many other works in the future for occluded ReID, was part-based pooling. So normally, given output from the last convolution layer, there is a feature map for a given person. We do a global average pooling and extract one single feature for the whole person. But they presented a method where we could actually extract stripes of information and pool only within these stripes. So each vector would be from different regions of the image, and they apply a separate classifier to each of these features. So by this way, it is a kind of learning self-attention for individual parts, and they work quite well with occluded ReID as well in compared to person ReID. And our next set of work after 2018, they started mostly focusing on different ways to mask the occluded region. And one of the and most of the papers were related. Sorry, just a minute. So most of the papers were related to using some kind of key point extraction or pose map or heat map to focus on non-occluded regions. So this work in sorry, I think there's a mistake in the slide. Okay, I'll just explain it based on the image. So Mao et al., they actually, and as well as another paper after that, they focused on using key point based feature extraction as well as pose based heat maps in order to focus on non-occluded regions. So basically, the Mao et al., what they did was they just used pose as an attention to focus on non-occluded region, and the papers that followed that started training their own visibility part visibility scorer based on pose estimation. So basically, Mao et al. During test time, they won't be using in test time they will just be using the attention alone, but the other papers they actually trained a separate classifier. In addition to having pose based attention, they also use a visibility predictor for each parts of the body. But as we've seen, since the methods that use, for example, the methods that previously did not use pose, it's a very straightforward approach, but it is not something that is very that is very much focused on occlusion. But the papers that came out later after 2018 and 19, they were very much focused on occlusion, but they needed external supervision like pose estimation. So these pose estimators were often trained on a separate dataset. And since it's a separate system altogether with its own CNN network, it adds to additional complexity as well as additional noise that would actually come from the system. So keeping this in mind, so we present our motivation here, where we observe that when we look at the distances of interclass and intraclasses for a holistic data, so by default, even with say by early stopping, we could see that we could have a good separation between the distribution of interclass distances. So inter meaning intra meaning within the same class and inter meaning between two different classes. But for occluded data, though they were from the same data set and from the same domain, and we just separated occluded data set alone, we could actually see there was a big overlap between the within class and between class distances. This observation was actually inspired by one of the previous work in the lab from our lab, that's by Jibril, where they used a similar method for a domain adaptation. But in our case, both of them, for example, in this particular image that we see, both the images are from the same domain. There is occluded as well as non-holistic data from the same domain. There is the same data set. But just by separating them, we could actually see that they actually had a big overlap. So the aim was actually somehow to use this as a cue to learn the separation very much like holistic data, so that hopefully they can have hopefully they can perform well in real world scenario. So we propose to extract features from occluded and non-occluded datasets, and we jointly learn them using student teacher network, and we learn an attention map. So the attention map, like we see, focuses only on non-occluded regions and thereby discarding occluded regions. So our main contributions are in the paper we empirically show that this discrepancy between the within and between class distances for occluded as well as non-occluded data, and we propose to use this discrepancy as a means to learn the overall distribution for occluded ReID. And from the experiments that we performed before, we could see that our method could perform very well on occluded ReID data. In fact, competitively with most of the state-of-the-art method, or even outperform some of them, in spite of not using any additional data such as pose and having a complexity same like a regular holistic data ReID. So this is our overall system where we have an encoder and a decoder, and basically it is set up like an autoencoder fashion. So in the first step, we focus only on holistic data training, where we train our network for identity loss as well as reconstruction loss. The reason why we focus on reconstruction loss, that is we try to train it like a denoising autoencoder, is for two reasons. One, when we use identity loss, it tries to learn only the most discriminative features and forgets the other regions. So when you look at the activation map, it's going to look at small regions. And this, as we've seen, this could actually be dangerous for occluded ReID because the most discriminative regions could get occluded. So by encouraging a reconstruction loss, or by training it like an autoencoder, it actually it was beginning to spread the activation across different regions of the body parts, and we're getting the network ready for occluded ReID. So in the next step, we use our holistic data as well as occluded data together. While the holistic data would be training the teacher model, and the occluded data would be training the student model. And we train them in a student-teacher model such that we learn attention for individual body parts of the occluded data in order to match the distribution of holistic data. So we fix the distribution of holistic data. We don't. So during backpropagation, we detach them from the graph, And the holistic data that is overlapping learns the distribution by attending to individual parts of the body. So for example, we see that the top half of the body is occluded. So therefore, the attention to the body parts in the top half is going to be low, and thereby we are actually discarding the occluded region for consideration during the re-identification. So basically, it's a little bit of math on that, where the first one is a reconstruction loss, and second one is a joint, and we show how we jointly train for both identity as well as reconstruction, and we determine lambda by experimentally. In the second phase, LD is a MMD loss within class and between class distances of occluded and non-occluded data. And we also find the global MMD loss between the features of the teacher and the student, so that the end-trained CNN performs equally well on holistic as well as occluded data. So we jointly train them with the overall loss function, so which is the identity loss as well as the distance distribution loss. And so a little bit on the maybe I'll just briefly explain the ablation study and not maybe all the rows here. So basically we try to see how much each module is contributing to the overall performance. We can see that just by training on the identity, we score identity only. We score on 59.15 of rank 1 accuracy, but identity and reconstruction itself already improves the performance by a big margin. So like we hypothesized in the beginning, using a reconstruction loss helps to spread out the activation in different parts. So even if discriminative parts are occluded, since activation is on different parts, we still be able to do ReID. And thereby, and after using MMD as well as our attention, we see that the overall performance, there's a big jump in the overall performance, and we get a rank 1 accuracy of 82.3. So we evaluate on occluded duo versus occluded ED data, and we see that compared to other methods, that is the last 28, 57, and 39, which use pose as well as different kind of external input in order, or like key points, in order to separate occluded from non-occluded regions. We see that we have a big improvement in the results, and keeping in mind that we did not use either the additional data nor any expensive process for processing the additional data. So the same goes to the occluded ReID as well. And also, I just want to show by the PCB is a part-based method where they did not really focus on occluded ReID, but just treat the individual parts separately, like we talked before. And even that seemed to help quite well compared to maybe a simple basic CN. And we also see that our method performs well on holistic data equally and competitively. And thereby we can see that our we could now adapt to both holistic as well as occluded ReID without having a gap in the result. So here are some of the qualitative results. What we see on the middle row, on the middle column is actually a heat map or activation map from one of the methods that use poses. There's the PGFA method, which use pose for selecting occluded and non-occluded region. And we can see that since the pose actually focuses only on smaller regions, so which is actually not quite desirable. In this image, it's fine, but in another image where the face is occluded, the pose could fail here. But we can see that our method actually spreads out its activation across different regions. And a good example would be this, where the pose actually made a mistake. So this guy here is carrying a water bottle and is covering his face. It's like a small water tank is covering his face, and we can see that pose made a mistake. Pose estimation made a mistake. It considered the water bottle as his face, but our method actually did not show good activation there, but it actually spread out to different regions, whichever was visible in the whole image. So to conclude, in order to train our method, we do not need any additional cues, and just by looking at the discrepancy in the distribution, we can learn in occluded ReID in a more unsupervised manner without having to really have annotation for the occluded regions. And during it's only during the training that we have a big network with a teacher and student model. But during inference, all that we need is the second half of the box that is in the dotted line here, where we just need the attention map and an encoder, and we don't need any of the other parts. So thereby, there's hardly any additional complexity in compared to regular CNN. So we could also extend this to other applications, because we actually kind of can compare this to either to curriculum learning or to soft labels for learning. It can be called curriculum learning because we originally start from an easy task of holistic ReID, and then we move on to occluded ReID, which is more difficult task. And secondly, the data distribution, for example, since occluded ReID has, it's possible that occluded ReID can have other identities in the given image. Like one person could be occluding another person, but having just one label to it, and we strictly let the network train on that label, is going to overfit the system. That could be one of the reasons why the results of occluded ReID are bad when we just use an identity loss. But by using a distance distribution that is actually from a holistic data, and we can see that there is already some overlap in the holistic data and it's not fully separated. So this kind of becomes a soft label for the separation. So it says the network, you don't have to fully separate, but at least have a minimum separation. And the future work for this is from another empirical study that we did. Unfortunately, I didn't show the results here, but we did an empirical study where we tried to change the batch size and see what is the influence of that on the overall learning. We realized that the bigger the batch size we had better results, but it was definitely limited by the size of the GPU. So the reason why this is happening is because the main assumption in this the whole learning process is that given a small mini batch where we have holistic data and occluded data, and we try to learn distribution from holistic to occluded, we assume that the holistic data is clean enough and it has got nice images with no overlap and no objects occluding them, or maybe no motion blur and or no excessive motion blur. But most of the holistic data, in reality, this is not the scenario. They have at least 10 or 15% of occluded data in them. So having a small size batch is not actually good enough to capture the whole distribution. So having a bigger batch captures the whole distributions of the holistic data together, and thereby helps the learning. We could actually extend this to we could probably extend it to maybe by using a dictionary-based learning, where we're able to capture the distribution of the whole data set via dictionary-based learning, and we could use that to transfer the data to the during occluded learning. And hopefully that will give better results, and we might not need to have maybe a larger GPU or many more GPUs to learn. And, that's it for my presentation. Thank you. Be happy to answer any questions.
Thank you, Madhu. Yeah. Are there any questions for Madhu? Please, Matthew. Oh, please go ahead.
Hi, Madhu. Thanks for this awesome talk. That was amazing. I was just, I really like this person re-identification. So like I got a couple of different questions, but like one I'm wondering about is like, comparing person re-identification to face recognition,
Yes.
Are the models quite different in the end? Could you maybe comment on that, the difference in the task?
No, actually they could be close because in face recognition, we assume that only a face is available. And of course, the kind of accuracy we expect is, since it's more of bioinformatics, the kind of accuracy we expect is much higher, but the overall system tends to be the same. So we have where we have the query gallery, and and during training, we might not have access to all the identities. So we just learn a generic feature representation learning with large identities, and we directly move to the testing phase where we have a set of query and we try to retrieve it from the gallery.
Okay, that's interesting. And so I'm just wondering, like, and how about the role of the occluded learning, the student-teacher learning with occlusion, stuff like that? Was that is that something that's done? Is broadly useful? Like for face recognition, or would that not be useful?
while doing the survey, we did come across a few methods for occluded face recognition, but it was mostly like adversarial approach or like autoencoder based self-recovery approach, but we didn't really come across something like this.
Okay, and yeah, one last question, like what's the if you're going to apply this this technique, like a lot of these images with occlusion, random umbrella, etc., that sort of makes me think that this would be applied and would be very useful in real time in identifying like people as they walk through a cluttered scene, etc., with occlusions. And so in that case, you might not have a lot of time for training. You know what I'm saying? You might not have a big training database for this specific person wearing this specific pants, in this, and so like, would this be work well on like, real-time application?
Actually, the main aim was originally focused on multi-object tracking. So because we started off with doing multi-object tracking, and we realized re-identification was like was an important step in multi-object tracking. And most of the research in the last few years were towards that direction, to have a very good representation for doing re-identification between camera frames. And then we realized that while working on person ReID, and because there wasn't really enough for multi-object tracking, because in real world multi-object tracking is mostly occluded. Most of the images were occluded, and because it's mostly clouded scenarios. So yes, this would be really useful in maybe in scenarios like applying it for multi-object tracking or maybe any other application.
Oh yeah, well that's interesting. So then it would be a challenge to train it, I guess, to recognize like a person wearing different clothes the next day or something like that.
Yes.
Like would that be challenging?
Yes, because right now in our assumption that has not been included, because
well, it's a general assumption. I mean, in ReID, they assume that you capture someone in one camera, and then you're identifying them as they appear in other cameras.
Okay, yeah. So it's a handoff, a type of pass-off thing of like roughly the same date.
Yeah.
Yeah, exactly.
It's not necessarily, the objective isn't necessarily to identify a particular individual as being Madhu or Matthew. It's being able to say, okay, well, we spotted someone and we also saw them over there in front of that camera,
So yeah, I see. Yeah. You're not identifying. Yeah.
I mean, to come back to your other question, it's a little bit different than recognition as such, because the objective isn't necessarily to recognize someone specifically, but as Madhu was saying, the structure of the system could be very similar, especially in the case of what they call face verification in biometrics, where really the preliminary step is to learn this kind of use metric learning to learn this kind of model that can compare similar people, and produce, in the end, like some sort of deep Siamese network that is able to take in two images and tell you if it's the same or different. And that's like a verification scenario in biometrics. And
yeah, I see. That's very interesting. Like, is this the same person or not? It would be fascinating to apply this to our brain data, where we're identifying, individuals and relatives, to see if this could be able to learn, some representation that could. I guess that would be more like metric learning in some ways.
It is. It's that. Yeah, it's that exactly. I mean, the training being Siamese network is metric learning. Yeah. And I've seen it. I've seen it, for example, applied in something very similar, but not with brains, where people do kinship analysis, where they're trying to recognize. I think the idea originally, I'm not sure how popular this application is the idea is to have a camera somewhere and be able to kind of identify people that are from the same family. And like one of the applications that was brought up to motivate this was that, for kids that have disappeared, or, that you'd be able to later on be able to recognize them as that or a member of the same family. But it's similar to your application in a sense, right? That you're trying to.
Exactly. Yeah, that's pretty much exactly it. It would be very interesting to see this. I mean, we tried metric learning on this data set that we have of brains, and it was not entirely fruitful. But we didn't spend a lot of time working on it like this either. So that's kind of it for me, but I'd definitely be interested, Madhu, in talking about this stuff a little bit later. And if it would be possible to apply it in some way to our brain data, that would be really great. Get some students to try it in my course. All right, thanks. Any other questions?
Thanks, Matt. Sorry for interrupting.
Yeah, thanks. No problem. Thanks.
Any other questions? No. Okay. I just want to ask as well. Like, did you compare the complexity? Because at the beginning, you're talking about this motivation that the techniques in literature are more complex because they rely, for example, on pose-based estimation to select occluded regions, and there's never any, we never come back to that and say, well, you know, our technique, okay, so you present the accuracy results and it looks favorable on that front, but what about the complexity? Is your approach, because these would be applied in real-time applications like video surveillance. So your system would be applied there. So what is the benefit in terms of complexity? Have you noticed anything there? Or?
I don't have anything in numbers directly, but compared to like a bare bone deep CNN based re-identification, which has just a backbone and absolutely no bells and whistles, we just have a few additional weights for individual parts. But comparing that to the pose-based methods, they have a separate like a deep network in addition to the ResNet backbone to extract pose maps and including the post processing and pre-processing and all that. So we definitely
it may be something to look into.
Yes,
just to close that question. You know,
sure.
on how complex our model is compared to, or
Sure.
This model is compared to posed estimation, for example. Yeah.
Sure.
Yeah. Another question. So how does it deal with, okay, so another big problem with this kind of system is you may have detection errors. Yes. So the front end of the system is a model that would detect people, right?
Yes.
And there may be a connection between the two systems, but assuming you have like a detector in front of you, this model, and it's producing, you know, bounding boxes with people in them, like how would it deal with the situation where there's a detection problem? Let's say it detects half the body, or it's not occluded, but it gives you a problem with the detection. Because I guess if you have a detection problem, it will give you body parts in different areas of the bounding box, right?
Yes.
Is your model robust or resilient to this, or not more than anything else, or?
Of course, we did not really evaluate on datasets or issues in particular pertaining to this, but it can work as long, because since we depend on part-based features and we extract strips from different parts of the feature map, and usually it goes from top to bottom 6 strips. So basically a size 256 cross 128. 128 is divided by 4 or 6. If there is, say, misalignment in terms of the height, say the legs appear in the top half and the bottom half is maybe ground or something else, that could be a problem. We could actually what we could do is, instead of arranging the strips in an order, we could actually try to find a certain rule, and we can try to stick to that rule. For example, we could something very similar to a radial basis function. We could have maybe clusters of the heads, body, and legs, like 3 different clusters, and we could actually see where different steps fall into. and we could rearrange the feature to actually follow the pattern.
Good. Okay. So I mean, that's something that could be an interesting thing to look into, I guess, because that would be a problem, I would think, because we would be focusing on the wrong parts of the body, I would think.
Yes.
Right? Because you're priming your model, but the question I was getting at is whether it would be robust or how much it would be affected by that problem. But okay, thanks. That was a good answer. There's also a question by Hamad, I think. Ahmad, sorry.
Yeah.
Well, you can ask it definitely, Ahmad. But he's asking you to explain the validation steps.
Okay. So validation, what we have different data sets, and these data sets actually have their own set of query and gallery. And basically, they give us a set of query and ask us to find which gallery image it matches to. And of course, the gallery images, all of them have a query and gallery, both have identity information as ground truth. And if the ground truth identity matches for both, then it is considered as a 100% classification. I think I hope that answers your question.
Does that answer your question, Ahmad? Yep. Okay.
Thank you.
All right. So are there any other questions for Madhu? So if not, I want to thank Madhu for the nice presentation, and I want to thank everyone else for attending, and I guess we will see each other in 2 weeks. The next one is in 2 weeks. I'm not sure who that presentation will be from, but it's so we're on a schedule now where we have a presentation every 2 weeks, and we hope to see you there as well. Okay.
Sure.
Thanks,
Thank you.
everyone.
Thanks, everyone. Bye now.
Thank you.
Great
Bye.
presentation.
Thanks. Thank you.
Thank you.
From the review was, yeah, it was my my doing, I think. Eh?
Sorry. Oh,
Anyway.
no, so no, actually, I didn't realize it. Sorry, I didn't realize that because I just saw the images, and even when I saw that, I didn't observe that change.
Yeah. Well, I guess one too many changes at the last second, you know.
Excuse me. Yes.
But yeah, I tried to split up the review because you had all the text and then all the images, so I tried to like break it up a little bit. But
No, it actually looked very good, to be honest, because it is categorized too. The first category is that doesn't use post, and the other category uses post. So it was.
Yeah, just somewhere there was a mistake in the cut and paste. But anyways, well done, and definitely was a good practice. You know, I think
For sure.
I think it's also in the type of questions you get. You know, I mean, but definitely like you got to, you know, say it once. You know, and it gets better and better. And I don't know what, about this other conference, the local one. I don't know how that works exactly. The one with, I think it's Mila that puts it on.
Yes.
But anyways, that's another opportunity just to practice and kind of
Sure.
see how it goes, and hopefully you get some questions that are smart and everything.
Sure.
Yeah, it looks good. I like it. So, okay.
So,
I have I have a PhD committee in a few minutes, and
okay.
I haven't eaten lunch, so I'm gonna go and run and do that.
Sure.
It was great, Madhu.
Thanks, sir. Thanks so much. Thank you. I'm happy it was a good practice. Thank you.
Take care.
Bye. Take care.